Hi there. Before we get started today, I want to do a quick little mental experiment. So if it is early in the morning uh, or very late at night and you need to wake up before we get into this very interesting chapter, maybe you can actually do this experiment. But if not, that's okay. It's just a mental exercise. So what do you predict will happen when you pour cold creamer into hot coffee? Okay, so is it going to instantly mix so suddenly it's all milky coffee? Is it going to have creamer just at the top? Is it going to swirl around and disperse? Is it going to hit the bottom first and then swirl around? What's going to happen? So if you are an avid coffee drinker and you enjoy creamer in your coffee, then you probably already know the first thing it does is sink to the bottom, and then it starts to swirl and mix. But the cool material sinks to the bottom, and then it finds an equilibrium. It disperses. So what does that have to do with Chapter 13? It has everything to do with Chapter 13, because all of the different things we're going to be talking about that have to do with climate and weather, all of it is relying on convection. And so that's what's happening in your coffee cup. The hot material rises to the surface, the cool material sinks to the bottom. So your cold creamer sinks to the bottom, the hot coffee stays on the top. And if you don't stir it around, sometimes if the temperature is just right, the creamer will stay on the bottom. But you can do this with all kinds of different things, and I encourage you to start experimenting and paying attention with fluids of different temperatures and what's happening. You know, when you walk into a room, is all of the cold air, does it seem to be at your feet? Is it hotter up toward the ceiling? That's convection at work. If you are cooking and you're using a convection oven versus a regular oven, what's the difference? So start paying attention and see that this is all around us all the time. So, Chapter 13, Climate and Weather, and their influences on geology. So this week and next week, this lecture is broken up into two pieces. So really, we'll make it through 7 pages in your notes today. There will be a quiz based on that material, and then next week I'll post the other half of the lecture. We'll get through the rest of the notes, and I'll post a quiz on that material. But ultimately, what I'd like to get through is that the atmospheric winds and ocean currents are linked together, and that they control the weather. I want to get across to you the causes of hurricanes, tornadoes, and storms, and I want you to understand what deserts and rainforests are, where they're located on Earth, and what does that have to do with global circulation. And then lastly, we're going to look at the evidence for climate change and get a good feel for that. So what do you already know about climate and weather? There are lots of things on the news all the time, disaster movies, things like that, and people that talk about climate that don't really necessarily know what they're talking about. So we're exposed to discussions about climate all the time, but we do all know a bit about it because we live in it, right? We live in the weather, and over our lifetime we get a feel for what the climate is if we stay in one place or if we travel around and observe the climates of different areas. So as far as what you know already about climate and weather, of course all of us are going to know different things, but hopefully you all know that it is changing, that the climate that was is not the climate of the future with the way things are going right now. And we'll look in more depth on the mechanics of that. And you know that climate is different in different places. And so what I think is really cool about this chapter is you can see where the similarities are found. That's pretty neat. So, to talk about this, we need to know what we're talking about. So let's define climate. Climate is an average of weather, typically taken over a period of many years. Okay. As opposed to weather, weather is a daily description of the temperature, pressure, and precipitation conditions of the atmosphere for a specific place. So I didn't underline those words just for fun. They are there to help you remember what they are. Climate is an average of weather over many years. Weather is a daily thing for a specific place. Okay, so if I ask a question that gives you the example of Phoenix is 80 degrees on November 10th. I want you to know that I'm talking about weather, right? Because it's a specific day, it's a specific place, and I'm talking about the temperature on that day. As opposed to climate, I might say that Arizona has an arid climate, meaning not much rainfall. Okay, and so that's an average over many years, generally over a wider area. And both climate and weather are responses to global circulation of water and air. So anytime you're talking about climate or weather, it's linked to everything else. It's linked to the weather and climate in other places around the world. Okay, so it's all connected because of this global circulation of water and air. So that takes us to a very good example in India. So let's observe this area and consider what different climates are likely to be present and what controls them. Okay, so take a minute and just look around. We've got along the Indian Ocean, so a beach environment. We've got some very arid looking places, the dry, brownish areas, so we've probably got some desert conditions. We've got some very high mountains, so that's going to give us a completely different environment. This is a perfect location to see many different climates going on in a relatively close area. So it's a good example because this region has the most extreme topographic changes on Earth. And they have massive rivers that carry sediments from the high mountains down to the sea. So from up in Tibet, from the Himalaya Mountains, all the way down to the Indian Ocean. India is surrounded by ocean on two sides, providing a profound influence on its climate. And that also contributes to winds coming in off of the ocean and up to the mountains. So the Himalaya Mountains have been thrust up because of the collision between India and Asia. It was a convergent boundary. It's still moving. The Himalayas are still getting taller. It's pretty amazing. And dust storms blow off of India's northwest desert. We have nutrient-rich waters because of algal blooms off the northwest corner of Africa. Okay, so that's this green swirl coming up in the water there. We have rainforests that cover many parts of the subcontinent. And floods. Floods are a huge problem there. Floods are common from the Brahmaputra River a massive fluvial system that transports tremendous amounts of sediment. So it's coming off of the Himalaya mountains and just trucking out like a huge conveyor belt, tons of sediment up from the very high mountains. So with all of these things together, we're looking at some very different climates, all in the same area. Alright, so that takes us to our next question in your notes. What causes wind? And what are the two most common gas molecules in the Earth's atmosphere? So our two most common are oxygen, O2, and nitrogen, N2. Okay, those are the most common gas molecules in the Earth's atmosphere. Okay, so we've got basically air is full of stuff, okay, and I don't mean dust and particles, although there's plenty of that. I mean, we walk around not paying attention to the air most of the time, right? Because we can't pick it up, we can't do anything with it. We're in it, and so we take for granted that it is made of all of these tiny molecules, and those molecules all together exert a force on the surface of the Earth, and that's what atmospheric pressure is. Okay, so the weight of these molecules exerts a force on the Earth's surface and on other objects like us. Pressure, which is calculated by the force divided by the area, is exerted in all directions. This is atmospheric pressure, the weight of the air above the Earth. So when you think about atmospheric pressure, think about the weight of the air above the Earth. And so pressure drops off as you gain elevation because there's less air on top of you. So when you drive up to Flagstaff and your ears are popping and you try and run down the street and you have a hard time breathing, there's less air there, literally, and there's less pressure pushing down on you. Okay, so changes in pressure from one location to another is what causes wind. I'll say that again. Changes in pressure from one location to another causes wind. Pressure can be measured in a device called a mercury barometer. As atmospheric pressure decreases, the height of the liquid mercury in the tube falls proportionally. It's not as common to use a liquid mercury barometer these days. Modern digital barometers measure very small changes in pressure, and so this can be extremely helpful in tracking storms and in tracking weather changes. All right. Which point has a higher atmospheric pressure here? Is it the location A that's up in the mountains, or is it location B that's down at sea level? Okay, so think again about what atmospheric pressure is. It's the weight of the air on top of it. So which location has more air pressing down on it? I did this little animation here to help anybody who's having trouble thinking about air as something with mass. So each of these bars is representing a unit of air. And so we've only got 3 units at A, and we've got 4 full units at B. So there is more air pressing down at B. The higher atmospheric pressure is at location B. Okay, and so we can predict what direction the wind would be blowing here because we have higher atmospheric pressure at B. than at A. We've got low atmospheric pressure at A. Air and fluids want to move from high pressure to low pressure, right? Just like during the midterm, you wanted to be done with that like nobody's business. You wanted to move from that high pressure state to a low pressure state. Okay, everything in nature wants to do the same thing. So it's almost like that high pressure at B is squeezing it down and pushing it over up towards the mountains. So we're going to have wind blowing from B to A in this example. And again, there's more air pressing down on point B, so the pressure is higher. How is sunlight distributed? So this one is kind of hard to explain without a marker board to draw this out and show you, but hopefully these graphics will help you. Is sunlight evenly distributed on the Earth's surface? So let's take a look at my little graphic up at the top. We've got our happy little sun with sun rays shooting at the Earth. It is most directly hitting at the equator, right at the center, that widest point on the planet there. So at that point, the sunlight is coming in directly. So now we're going to look at the image just below that. So this is where the sun is overhead, and we've got sun beating straight down. Okay, so the further away from the equator you get, and the closer towards the poles, the sun is coming in at a greater angle. Okay, and so that means less sunlight is coming in, and that's our example on the right. Okay, so is sunlight evenly distributed on the Earth's surface? No. There's more sunlight at the equator than there is at the poles. Okay, and so that answers the next two questions. Where is sunlight concentrated the most? At the equator. Where is sunlight concentrated the least? At the poles. And how does the sun angle affect the amount of heating on the Earth's surface? The greater the angle, the less sunlight reaching the surface. The greater the angle, the less sunlight reaching the surface. So as it's passing through the atmosphere there, it's losing energy, it's losing heat. So at high latitudes, the Earth's surface is unfavorably angled to incoming rays. So if we look up towards the pole, that little yellow beam is representing the angle at which the sun is hitting the atmosphere, and then it's got that very long distance to go, as opposed to at the equator towards the center of the Earth, it's just coming straight in. It doesn't have to worry about that angle, and so it's traveling a shorter distance. More heat is reaching the equator. How does air move around a high and low pressure system? So we've got several differences here between high and low pressure systems. Starting on the upper left-hand corner here, high pressure systems have a relatively high atmospheric pressure. Surprise, surprise, right? That's why it's called a high pressure system. So what I mean by that high pressure is the air is pressing down on the surface and exerting a pressure on the Earth's surface. Okay, so it's associated with sinking air and fair weather patterns. Okay, fair weather patterns mean it's dry. And in the northern hemisphere, high pressure systems rotate clockwise. Okay, so again, a high pressure system has high pressure. It's associated with sinking air. So the air is descending, it's pressing down on the Earth's surface. We have fair weather patterns, and it rotates clockwise in the northern hemisphere. Okay, low pressure systems are just the opposite. They have relatively low atmospheric pressure because the air is rising. Okay, so you can imagine picking the air up off the surface. Okay, if the air was somehow like a weight, and you could just pick that up off the surface, that would be what a low pressure system is like. The air is being lifted up off the surface, so the Earth's surface is undergoing less pressure. It's a low pressure zone. So it lifts, and cool, moist air triggers unsettled weather patterns. So what I mean by unsettled weather patterns is you have rain and storms and things like that. So low pressure systems are associated with, something's coming. You know, maybe it's a tornado, maybe it's a monsoon, maybe it is a hurricane. Anytime you have rain coming, that's considered an unsettled weather pattern, and that's associated with a low pressure system. So it rotates counterclockwise in the northern hemisphere. Okay, so again, a low pressure system has relatively low atmospheric pressure. Air is lifting up off of the surface. It triggers unsettled weather patterns, meaning storms, and it rotates counterclockwise in the northern hemisphere. Okay, so I've answered several of these questions, all in my going on and on. So how does air move around a high pressure area in the northern hemisphere? It descends and rotates clockwise. How does air move around a low pressure system in the northern hemisphere? The air rises and rotates counterclockwise. How is this different in the southern hemisphere? Okay, it's the opposite in the southern hemisphere, just the direction of rotation. So just like you've probably heard that when you cross over the equator, toilets flush the opposite direction, right? The Coriolis effect gives us everything rotating in a certain direction in the north, and then it rotates the opposite in the south. So rotation is reversed in the southern hemisphere as air moves away from the equator towards the pole. We're going to go into great detail on why it reverses like that. So just retain that curiosity. Okay, so this brings us back, this next question here brings us back to what I mentioned on the last slide. On the Earth's surface, air moves from areas of what to what? Okay, so it should be from areas of high pressure to areas of low pressure. Alright, and we've got a couple ways to look at global wind patterns here. Okay, I'm going to show you the most basic one first, and then I'm going to elaborate on that. So for this one, we have this yellow arrow coming in on the left. That indicates the lighting direction from the sun. Warm air is heated at the equator and rises up and flows north and south. So it's moving from the equator towards the pole, whichever side it's on. As it rises, it cools, descends, and flows back toward the equator, forming a belt of easterly winds around the equator. The flow from the equator is not straight north or straight south, but ends up being deflected as the Earth rotates. And the equatorial regions get heated more than the poles, setting up an overall flow of warm air away from the equator and of cold air away from the poles. Okay, so flow gets deflected by the Earth's rotation, and this is what gives us our prevailing winds in that area, either westerlies or easterlies. Alright, now here is the more text-heavy version of this with a couple of video links to help you out with this. The previous one has all the info you need to fill in those boxes. But this information is important anyway. Okay, so the Coriolis effect is the effect of air and water rotating. So the spinning globe has a higher spin velocity at the equator. So air moving north or south is deflected to the west due to rotation. So either if you're north of the equator or south of the equator, it doesn't matter. Because of the rotation of the Earth, it's all getting deflected towards the west. Okay, and what I mean is having a higher spin velocity is the Earth is traveling at the same speed, right? It's rotating at a certain speed. And all of it goes the same speed. But at the center, you can imagine if you, if this was like your hamster ball and you're running around inside of it, you would have to run a greater distance if you were at the center of the Earth, right? If you're along that widest point at the equator, there is a larger distance to cover in the same amount of time than it is at the pole, where you could just sort of spin around the little pole and you wouldn't have to go very far. So hopefully that makes sense. And if it doesn't, these videos are really good at giving you a basic visual of how this works. Okay, differential heating is what I was talking about with different levels of sunlight hitting the Earth at different places. The equator receives more heat, creating bands of warm air wrapping around the globe. And that is the engine here for all of this circulation, the global circulation of wind and water. So air rises and flows away from the equator. Hot air rises and moves towards the colder part, which would be the polar regions, while air at the surface flows back toward the equator. So these are getting at the idea of flow cells. So flow cells, rising and movement away from the equator and superficial movement back creates large tubes of moving air. So that's what we're talking about when we talk about flow cells. Okay, convection cells. I've already mentioned convection quite a bit, but convection cells describe the flow of materials with temperature differences. Okay, so what is a convection cell? It describes the flow of materials with temperature differences. Okay, so you've created a convection cell in your coffee cup. When we were studying plate tectonics, we were looking at convection cells that were moving these huge plates from convection within the Earth. Okay, how does air move in a convection cell? Well, that's what this image is showing us. We have warm, moist air rising, and we have cool, dry air descending. That's how air moves in a convection cell. Warm, moist air rises, cool, dry air descends. Okay, and so when we have warm, moist air rising up, we're lifting the air up off of the surface, creating low pressure. When cool, dry air is descending, that air is pressing down, sinking to the surface, building up a high pressure there. Okay, and I've already written in the high and low pressure here, but go ahead and look at your convection cell graphic in your notes and write, draw in your arrows, and write in the high and low pressure. What weather is associated with a high pressure area? So if we have cool, dry air descending in a high pressure area, that tells us that we have fair weather. Okay, it's dry, it's not stormy, clear skies, that sort of thing. The weather associated with a low pressure area, though, When we have warm, moist air rising, as that vapor rises up, it cools off, and so that's forming clouds, forming rain, maybe snow or hail. So a low pressure system is associated with storms of all types.